Imagine stepping out an airlock into a vacuum where the sun burns with unfiltered fury and the shadows are absolute, soul-crushing black. You are technically walking on the surface of a tiny, pressurized bubble, a suit that is essentially a personal spacecraft tailored to your own body. Most people look at an astronaut and see a hero, but we look at that suit and see the most complex garment ever stitched together by human hands. It is a machine that maintains life in a place designed to kill you in seconds. But here's what nobody tells you. This miracle of engineering starts not in a clean room, but deep within the industrial belly of our own planet. Think about the sheer scale of the materials required to fight the vacuum of space. We are talking about liquid-cooled underwear woven with miles of plastic tubing, layers of orthofabric to resist micrometeoroid impacts, and multi-layered insulation that looks like crumpled kitchen foil but protects against temperatures ranging from 121 degrees Celsius down to minus 157 degrees Celsius. You might think this is all high-tech synthetics, but the origin story begins with raw, gritty extraction across the globe. Some of these materials begin their journey in the specialized chemical plants of Germany, while others start as refined polymers from the oil fields of Texas. And this is where it gets truly extraordinary. The path from a raw polymer bead to a pressurized life support system is a journey of thousands of miles and microscopic precision. Most people never think about the sheer amount of work that goes into just one layer of the suit's composition. Take the thermal micrometeoroid garment, or TMG. It is the outermost shield of the suit, built from a proprietary blend of Nomex, Kevlar, and Gore-Tex. The Kevlar fibers are extracted in specialized facilities in the United States, utilizing high-pressure polymerization that pushes the limits of structural chemistry. We aren't just talking about fabric. We are talking about material with 5 times the strength of steel per unit of weight. The environmental footprint of producing these specialized fibers is massive, requiring thousands of gallons of water and precise chemical stabilizing agents to reach the 99.9% purity required by NASA. What happens next, however, is a process of assembly so fragile, one microscopic speck of dust could lead to a catastrophic pressure leak in orbit. Once the materials are sourced, they arrive at a secure facility where the climate is controlled to a relentless 21 degrees Celsius and a humidity level of exactly 45%. Any deviation in the air quality and the glues, epoxies, and seals won't cure properly, leaving the suit vulnerable to structural failure. The manufacturing process begins with the bladder, a pressurized layer of urethane-coated nylon that must hold a pressure of 4.3 psi against the crushing vacuum of space. It is heat-sealed at temperatures reaching 180 degrees Celsius, with operators monitoring the seams using ultrasonic sensors. The sound here is a constant, rhythmic hum of industrial ventilation and the hiss of pneumatic presses. You can smell the faint, sharp tang of ozone and synthetic rubber hanging in the air. The complexity ramps up when we reach the liquid cooling and ventilation garment, which is essentially the suit's circulatory system. This is a mesh of 300 feet of thin, medical-grade polyvinyl chloride tubing that must be hand-stitched into a form-fitting spandex garment. Imagine threading a needle for 8 hours a day, knowing that if one of those tubes kinks, the astronaut will overheat within minutes during a spacewalk. Workers use specialized jigs to ensure the tube spacing is consistent within a tolerance of 0.5 millimeter. It is a grueling, repetitive task that requires the steady hands of a surgeon combined with the patience of a watchmaker. But what is truly terrifying is that this entire cooling network is tested by pumping pressurized water through it at 25 psi. If a single bubble remains in a line, the whole system has to be scrapped. Now, look at the hard-shell components. The torso, the shoulder bearings, and the helmet ring. These are carved from aerospace-grade aluminum and titanium using CNC machines running at 15,000 revolutions per minute. The process takes 48 hours of continuous machining to turn a solid 200-pound block into a 15-pound skeleton. It's a violent, high-speed dance of carbide steel against metal, bathed in a constant stream of cooling fluid to prevent thermal deformation. The air here is thick with the scent of machining oil and heated metal. Each part is then measured by a laser scanner accurate to 5 microns, a distance thinner than a human hair. And if the machine identifies a single deviation beyond that tiny window, the part goes straight into the recycling bin, costing the factory tens of thousands of dollars in a split second. Quality control for a spacesuit is not just a final step. It is the entire purpose of the existence of these factories. Every single stitch is photographed by AI vision systems that compare the finished product against a perfect digital twin in the cloud. We subject the suit to a vacuum chamber torture test, where we drop the pressure to zero and keep it there for 24 hours. The suit must maintain an internal pressure of 4.3 psi, checking for leaks that would be invisible to human eye, but fatal in orbit. We also perform a drop test, where the suit is impacted by high-velocity aluminum pellets traveling at 7 kilometers per second to simulate orbital debris. It is a brutal, unforgiving gauntlet that only the most resilient suits survive. Globally, we are only producing a handful of these suits every year, with the total market for EVA-capable suits sitting at roughly $200 million annually. While the United States remains a leader with nearly 50% of production capacity, Russia and China are rapidly scaling their own indigenous programs. We are seeing a shift where the workers who build these aren't just seamstresses. They are aeronautical engineers, chemical technicians, and software specialists. Employment in this sector is highly niche, with fewer than 5,000 people on the entire planet qualified to certify a spacesuit for flight. The stakes have changed, too. We are moving from short-duration missions in low Earth orbit to the long-term, high-radiation demands of Mars and the Moon. Did you know that the pressure inside a spacesuit is so high that if it weren't for the rigid structural joints, the suit would balloon out like a giant balloon, making it impossible for the astronaut to move their arms or legs? Another shocker. The suit's gloves are the most expensive part of the entire assembly, costing over $70,000 per pair because of the extreme mobility required to manipulate tiny fasteners in space. And perhaps the most surprising fact of all is that the suit is actually more of a space plane than a piece of clothing, containing its own radio, oxygen scrubbers, power supply, and waste management systems. It is an independent, self-contained, and perfectly synchronized environment that keeps the human heart beating against the backdrop of an infinite, uncaring void. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the Earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.